We'll start by drawing a sketch of a right triangle, and by definition, a right triangle has one 90-degree angle, which is also referred to as a right angle, and it's designated by a box. The other two angles, by definition, are acute. And the hypotenuse is always the side that is opposite of the 90-degree angle. Now, we'll pick one of the acute angles and label it theta for our problem. And then we can define the other two sides relative to the angle theta that we picked. The side below angle theta, which is right next to angle theta, is called the adjacent side. We'll label that ADJ. And the remaining side of the triangle is across from the angle, and that is called opposite. And we'll label that OPP. Now we can apply the information that we're given in the problem using the definition for the tangent function. Tangent is defined as the opposite over the adjacent side. And we're told that that is equal to the square root of 3. Now, the square root of 3 can be written as an equivalent rational expression as the square root of 3 over 1. So we can more clearly see what numbers we can use to label our diagram. Square root of 3 is the opposite side, and 1 is the adjacent side. With this information, we can use the Pythagorean theorem to calculate the length of the hypotenuse, because we're going to need that to define the other trigonometric ratios. So the Pythagorean theorem is the hypotenuse squared equals the sum of the squares of the other two sides in the triangle. Adjacent squared plus opposite squared. Now we'll solve for the hypotenuse. So we'll take the square root of both sides and fill in the information from our triangle. The adjacent side is 1 squared, and the opposite side is the square root of 3 squared. That equals the square root of 4. That equals 2. And we can now label our diagram. The hypotenuse has a length of 2. That completes our diagram, and it's all the information we need to define the other trigonometric ratios of angle theta in the diagram. And we'll start with cosine theta, which by definition is equal to the adjacent side over the hypotenuse. So all we're going to do is refer to our diagram and pull out the numbers. The adjacent side is 1, the hypotenuse is 2, and that's our ratio for cosine theta. Similarly, sine theta is defined as the opposite side of the angle theta divided by the hypotenuse. And from our diagram, we see that the opposite side is the square root of 3, the hypotenuse is 2, and that is our answer for sine theta. Now, the remaining 3 trigonometric ratios are inverses of the 3 that we've already defined: tangent, cosine, and sine. We'll start with the cotangent, which is the inverse of the tangent function. So looking across right from our tangent function, we see that's opposite over adjacent, or we could say 1 over tangent theta, and we can just flip our definition for tangent, and that's adjacent over opposite. And that gives us 1 over the square root of 3. And we have to take the additional step of rationalizing the denominator by multiplying by the square root of 3 over the square root of 3 to eliminate the radical in the denominator, and that leaves us with the square root of 3 over 3 as our answer for the cotangent theta. Similarly, the secant and cosecant functions are just the inverses of the cosine and sine functions, and we will start with the secant. Theta is the inverse of the cosine. Theta, so we can flip adjacent over hypotenuse, and that gives us hypotenuse over adjacent, and that is 2 over 1, which equals 2. And the cosecant of theta is equal to the inverse of the sine of theta. So we can flip opposite over hypotenuse to get hypotenuse over opposite, and that equals 2 over the square root of 3. And if we apply the same procedure to rationalize the denominator as we did for the cotangent function, we're left with 2 square root of 3 over 3 as the cosecant function. And that is all 5 of the remaining trigonometric